Hi everyone, welcome to my channel where we make chemistry concepts simple and exciting. So today we are diving into the fascinating world of reagents. One of the important reagent is N-Bromo-Succinimide, commonly called as NBS, and its application in bromination reactions. So now let's get started. Structure and introduction of NBS. So NBS is an powerful brominating and oxidizing agent. So when we look up to its molecular structure, it consists of a succinimide ring, which is attached to a bromine atom, and it is widely used in organic chemistry due to its selective bromination capabilities, particularly at allylic and benzylic positions. Now here you can see I have shown a succinimide ring, and where NBS is nothing but the bromine atom is attached to the nitrogen directly in the succinamide ring. So the name is N-Bromo-Succinimide, which is in short form called as NBS. So next, let's look up to its synthesis, how it is prepared in laboratory conditions. So now NBS can be prepared from succinimide and bromine in the presence of sodium hydroxide solution, and what we obtain is a white crystalline precipitate called NBS. So during this synthesis, the temperature has to be maintained at absolute zero. Since if the temperature is maintained above 0 degree, or else if the reaction mixture is heated, the bond is cleaved, and it becomes amide. So to avoid or to protect the amide cleavage, we maintain the temperature of the reaction at 0 degree Celsius. So as I said, it is a very good oxidizing and brominating agent. So particularly at allylic and benzylic positions in a reaction. So first we'll learn what are allylic and benzylic positions. Yeah, the first one is allylic position. Here in this given structure, the allylic position is nothing but a carbon atom adjacent to double bond is known as allylic position. So in this given structure, you can see this particular position is called as allylic position, since it is attached or it is adjacent to the carbon atom containing double bond. In a similar way, if the carbon atom is adjacent to the benzene ring, it is called as benzylic position. Here, this position is called as benzylic position or the benzylic carbon, since it is adjacent to the benzene ring. Next, the synthetic application of N-Bromo-Succinimide. The most the mostly used applications of NBS is in allylic and benzylic bromination. This allylic and benzylic bromination is also known by a name Whole-Ziegler reaction, which is a named reaction. So before going to the reaction, let's look up to its mechanism. Yeah, mechanism. The mechanism takes place through a free radical mechanism. Here, when the NBS is reacted with free radical initiators such as AIBN or peroxides, or in the presence of light, or in the presence of Cl2, which is an halogen, it breaks down to form radicals, so that initiates the reactions. So as you can see here, there are four steps involved in this mechanism. The first one is the addition of AIBN, which is a free radical initiator with our N-Bromo-Succinimide. As we can see in the first step of this reaction, the reagent NBS is added with AIBN to generate a bromine radical by the dissociation or cleavage of this nitrogen and bromine bond. Here there is a formation of bromine free radical by the homolytic cleavage of nitrogen and bromine in this NBS structure. So then at the first step we'll get succinimide radical and a bromine radical. This bromine radical formed in step 1 is carried to the step 2 which where it abstracts the hydrogen from the allylic group. So there's a formation of a allylic radical which is a resonance stabilized, and the small amount of hydrobromide is formed. And this radical which are and again in the step 3 you can see that the hydrobromide is cleaved homolytically, and there's a formation of bromine radical in the presence of succinimide radical, so that there's a formation of succinimide again, and there's a generation of bromine radical. This step 3 is a most important step, since it is the initiation. This step carries out throughout the reaction until and unless this N-Bromo-Succinimide is completely utilized. So as the last step you can see there's the radical which is formed at step 2. The allylic radical formed reacts with the bromine atom, which is atom, and forms a radical. And then there's a formation of or the bromination of allylic. Allylic bromination takes place with the formation of a free radical, that is bromine free radical. So now after studying the mechanism how it happens, now let's see the examples for allylic bromination. So now first, in this first reaction we have an allylic group, and if I add NBS to it, here you can see the allylic position here is CH3. So the bromination takes place exactly at that position, since that methyl group is attached to the carbons having double bond, which is an allylic group. So the bromination takes place here, and so similarly here we have another example where we have two allylic groups or two allylic positions. So now if I add NBS to this type of structures, there's a possibility that the bromine radical can abstract the hydrogen from this methyl group, and it can also abstract the hydrogen from this methyl group. Since they have given 1 mole, or if it's not mentioned it's taken as a 1 equivalent, only one position can be attacked. So our product can be our product can be either CH2 Br CH1. Our product can be this, or it can give it can brominate at both the positions. But now here, since there's a mention of only one equivalence, we can get a product as this one or these two. And similarly, if 2 moles of NBS is given here with for the same structure, and if you can see there's a bromination taking place at both the positions simultaneously, since there's a 2 mole of NBS. Now let's look up to the another example which I have written here. Now let's look up to this example, which is a very important one. Since we can see here, it's an there's a carbon atom containing double bond, and there is two adjacent groups which are attached to it. So we have two allylic positions. Now before going to this, let's see the reactivity order. That is the CH2, that is methylene, is more reactive than methyl group, since methylene has two lone pair of electrons in it, and it is very unstable. So as we know, the unstable molecule readily reacts, and it becomes highly reactive, and whereas our CH3 is stable compared to CH2, hence it is stable to some extent than CH2. Hence in this reaction you can see there's a bromination taking place at this methylene carbon at allylic positions, not to the methyl. So this is all about the allylic bromination. And as I said, the next application of NBS is benzylic bromination. So as I said, the adjacent carbon atom which is attached to the benzene ring is called as benzylic carbon or benzylic positions, which is this one. So in this presence of NBS, the bromination takes place at this position by the abstraction of hydrogen. And the similarly, the second example we have two benzylic positions here. You can see this carbon is directly attached or it's adjacent to this benzene ring, and this carbon atom is adjacent to this benzene ring. So now we have two benzylic positions. One is here and the another position is here. So now the bromination can be taken place in this position 1 or this position 2. So since, as I said already during the allylic bromination, if there's nothing mentioned, you can take it as one equivalent and you can brominate at these positions, that is at 1 or at the position 2. So you'll get a product as A or it can be B. So if it's mentioned there's 2 mole, now you can add bromine radical to this both the positions simultaneously so that you don't get confused with single equivalent of NBS and two equivalent of NBS. When two equivalent is given, there's simultaneous addition of this bromine radical by the abstraction of a hydrogen, whereas when it's only one equivalent is given, either our bromine radical can attack to this position 1 or to this position 2, as we can see here, that is A and B. So the next example is similar to that of the first example. So here we have the benzylic position here, since this carbon is attacked or attached directly or it is present adjacent to this ring. After the addition of NBS, our bromine radical is added to this benzylic position so that we'll get this brominated product. So this is all about benzylic and allylic bromination. So the things which you have to remember here is our NBS is a most important use of this NBS reagent is in allylic and benzylic bromination. So in allylic and benzylic bromination, the NBS reacts with alkenes and it replaces the hydrogen atom at allylic or in a benzylic position. So with the bromine atom, similarly, you can observe that in benzylic position also it abstracts an hydrogen and adds the bromine radical. So these reactions are very controlled and efficient. By using this NBS, we can make a very effective bromination at these two positions. So, and at last, you should also remember that allylic and benzylic bromination is known by a named reaction called Cole-Ziegler reaction. Cole-Ziegler reaction. So this is all about NBS reagents which are used in allylic and benzylic bromination. So as I said, there are also other uses of NBS. That is, as you can see here, NBS can also be used in alpha bromination of carboxyl derivatives or carbonyl derivatives. So now moving on to these reactions, you can see that NBS facilitates alpha bromination of carboxylic acid derivatives, and in this reaction, there's an involvement of replacement of a alpha hydrogen atom which is adjacent to the carbonyl group. As you can see here, we have the allylic positions here and here. You can add the bromine radical to this position or to this. So now we have a cyclohexanone which is a ketone, which is one of a carbonyl derivative. So when NBS is added to this NBS replaces one of the hydrogen atom and replaces it with bromine, and cyclohexane is converted into 2-bromo-cyclohexanone. So this is about alpha bromination of carbonyl derivatives. Similarly, you can carry out the reaction using NBS with the carbonyl derivatives such as aldehydes, and also to some extent you can also carry out with acids, that is carboxylic acids. Now let's look up to the next application, that is allylic bromination of unsaturated compounds. While we say unsaturated compounds, you can have esters, acids, ketones, and other things. So NBS in this bromination of unsaturated acids, esters, aldehydes, and ketones. So these reactions occurs at allylic position of the double bonded systems, producing products that serve as the intermediates in pharmaceuticals and polymers. So what happens here is NBS makes bromination at allylic and benzylic positions, as we saw already. But here the products the products which are produced also serves as intermediates in the field of pharmaceuticals and while manufacturing the polymers. So let's not go deep into that. Instead, we can see here. Now we can see there's a presence of ester. I have taken an example of allylic ester. Now it is known as ethyl 2 butanoate, which is reacted in the presence of our NBS reagent. This CCl4 mentioned here is a solvent, or you can use benzoyl peroxide also as a solvent. Now, what does this do in this reaction is same as that allylic bromination. You can see there's a adjacent carbon atom attached to this double bond. So this can be our allylic position. Now there's nothing much. The bromine radical replaces the one of the hydrogen and it gets added to this CH2. So this is all about allylic bromination of unsaturated compounds. Next, in the similar way, we can see the bromination of aromatic compounds. Here I have taken the example of thiophene, which is also a five-membered ring. You have five-membered heterocyclic compound, heterocyclic ring. So now when thiophene is subjected to reaction in the presence of NBS, so as I told you that CCl4 and or you can use acetic acid as solvents. In this solvent, when NBS and thiophenes are reacted, we'll get 2-bromothiophene, where this position is in this position the hydrogen is replaced by our bromine radical to give 2-bromothiophene. So bromination of aromatic compounds, you can convert this, or you can add the bromine. You can add bromine to the natural products or heterocyclic rings such as thiophene, furan, and some to some extent like pyridine. So finally, this NBS reagent can assist in bromination of aromatic compounds with right catalysts. So I have not mentioned this catalyst here, but if a catalyst is given, the same thing happens but at a faster rate. So in this video, we have studied about the NBS, and so let's recap what we have studied. That NBS is a versatile reagent that plays a key role in allylic and benzylic bromination, also known as Hole-Ziegler reaction. And next, alpha bromination of carboxylic derivatives and bromination of aromatic compounds. And it is also a go-to tool for chemists around the world for brominating these type of reagents. So now we have learnt about NBS, and in upcoming videos we are going to learn about other reagents which are commonly used in our organic reactions. So for this video, only this much is enough. Let's explore chemistry together. Thank you. Thank you. Hey, Okra. Sakko.